Okay, well, numbers are still creeping up, but I think we'll make a start. So welcome to the first BPHO Computational Challenge uh, uh, run by Dr. Andrew French. We have run this session, these before, and they've been quite successful. One may possibly expect that the numbers drop off week by week. So are you going to be one of those people who have a bit of staying power? Well, I hope so. And what you need to be doing is jotting down some notes in a notebook. So have a handy notebook or at least some sheets of paper so you can jot down some ideas. If you don't do that, it's very hard to keep track. Just sort of follow every detail that's going on, which is very difficult. So don't be worried if you kind of start to kind of lose touch at places. What you'll have to do is kind of reconnect again and see what the overall ideas are. You should have downloaded the materials from either the BPHO webpage on the Computational Challenge or Dr. French's Eclecticon site. You'll find this year's sessions there as a large zip file. So download it, unpack it, and there are some exercises for you to do each week. They're not so long exercises, but they're there to sort of try and give you a chance to sort of just recap some of the ideas that Andrew goes through. So do feel free to ask questions. If you ask lots of technical questions, we may struggle to keep up, but we'll do our best. Ask questions in the Q&A, and we'll reply as best we can, because there are rather a lot of you. Links from us will be put in the chat for general availability. But in fact, I'm not sure you need a link at the moment. The BPHO website is on the BPHO website, so you can find that. And the Eclecticon is in its usual place. It's up there now. So as long as you haven't joined right this last moment, you'll be able to see those links. Welcome, and let's make a start. Thank you very much.
Okay, thank you, Robin. Good evening, everybody. My name is Dr. Andrew French, and welcome to the Computational Physics Challenge 2024. So, happy New Year, everybody. I'm going to go and hopefully, can you just confirm, Robin, you can see this little screen?
Yeah, looks
wonderful.
Perfect.
So,
let you know if it all disappears.
So, we're going to have a brief introduction about what this challenge is. And then we are going to sort of begin our first session. So for those keen beans who've come for the last year, or perhaps the last 2 years, this is the third year of the challenge. It's a slightly different format this year. So, however, the actual challenge format is the same. So what we got, what and how? We've got 10 one-hour weekly seminars from today all the way until April via Zoom. Each one is going to be completely independent. So don't worry if you miss one, but it'd be obviously awesome if you can if you can continue to come to everyone should be exciting. So as Mr. Hughes has mentioned, we've got a BFO website and my Eclecticon where you can get resources. So I think the best way of interacting with this stuff is to download the presentations. And basically we're going to use these talks as inspiration. So we'll have maybe about 10 or 12 different mini projects that we'll talk about. We'll illustrate different areas of physics. And I might make some hints of the kind of things you might want to investigate between the sessions. So each session is a bit like the challenge itself. So we're going to set a challenge, which will be after the sessions. This will be in April. And although I said September there, I think the actual deadline will probably be the middle of August. So you've got several months to do a project. This isn't an examination. You can work in pairs. So the first year we had a project on modeling the atmosphere. Last year, we had a project on modeling sort of solar system orbits. And I will release a set of recipes for all the stuff. All the physics is there. But you can code this stuff up using whatever language you want. So that kind of creativity is up to you. And the output is a 2-minute unlisted YouTube video, which you send to us. And that basically sort of shows how you solve the problems. And depending on the number of problems you do and how you do it, we will award a bronze, silver, or gold. So some challenges are sort of quite easy. They're a bronze challenge. Other challenges are much more involved, and that will get up to gold. And there's lots of extensions as well, if you wish to be competitive. I think the top 5 will get invited to the Royal Society for a nice ceremony. Well, the Royal Society, you can't really get much better than that. So there we are. That's the challenge. That's how it works. So why are we doing this? So think of a modern profession that does not involve the use of computers to create, record and store information, control machinery, etc. I'm not sure I can actually think of one. Maybe some of you can, but pretty much everything is some sort of symbiosis with machines. So there we go. This is our image of the bookkeeper Van Dyke here. I've got some quill, some paper and a sand timer. Lots of good things you can do with sand timers. If you came to the BFO round 1 training earlier this year, though perhaps given what he's wearing, some central heating would be quite nice. Why are we doing this? Well, basically, data flow. So how you take information from sensors and do things with it, how you process that data, how you present information in a meaningful way to humans or possibly artificial intelligence. This is a really vital element of the scientific craft. Okay, so at the moment, what have you probably experienced in science? You're probably doing theoretical problem solving. You'll be taking notes in your classes. You'll be performing lab experiments. You'll be preparing for exams, all that good stuff. That's all excellent. But that really isn't exactly how things work in the real world. It's about applying your science. It's about solving problems that may not have an answer in a textbook. You may be creating the sort of theoretical machinery. So this is kind of what this course is really all about. So if you look at the pictures at the bottom, we've got a model of a pendulum here, with the length of the pendulum, the angle, the mass, the velocity, the height, etc., etc. We might make a model in Excel, or perhaps take some data from a pendulum into Excel. We might then process that with something like MATLAB or Python or JavaScript or C or a myriad of other languages to automatically produce a graph. Here's a nice graph, the pendulum period versus the length, which for those of you who study this, it goes as the square root of the length of the pendulum, hence that's a square root curve. I've got some data points, and if you look carefully at your screen, you might see some error bars as well. So this is the kind of thing that we can automate mandrolic, boring tasks, because computers are really rather good at that. But humans have amazing reasoning, particularly in visual processing skills, and we want to maximize that. Okay, so real scientists will spend most of their time on data flow, data processing, and information presentation, right? So you want to start learning these skills fairly soon. And well, it depends on how you view life, but I think you'll want it to get a job. What would be great if a good section of you are fancy doing physics or applying maths and physics, STEM subjects for the rest of your life. It's a brilliant idea. And at the moment, it's pretty well paid too, but you need the right skills. So if you think of little companies like Amazon, Google, Uber, Meta, Tesla, Netflix, well, they like disrupting the traditional industries. Now, there's a lot of ethics. We can have a very different discussion about whether that's right or wrong, but that seems to be the zeitgeist. So in other words, if you don't have these kind of skills, it's unlikely you're going to get a job with these industries. And you never know, if you don't like those industries now, you could try and transform them. But in order to do that, you will need these skills. So there we go. So there's kind of an idea of it's not just about learning physics. It's about having the craft so you can do things with physics. And you will have a lot more fun at university if you have those skills. So not just learning stuff from lectures, but actually making models, simulation, processing data, etc. So even if your horizon is how can I get a distinction at A-level and get into top flight university, these are a great way, scientific computing skills, brilliant way to consolidate your subject. And that's the kind of topic of the book I published a few years ago called Science by Simulation. The kind of idea is that if you build computer simulations, this is a really, really good way of learning about mechanics or electromagnetism or thermal physics, whatever your topic, okay? So making things yourself that work is, I think, the best motivator for learning stuff, all right? And that does mean things are not going to work at the first go. You're going to have show some grit and resilience, fix bugs and all of that kind of stuff. But that really will build your confidence. So if you've never done any programming before, that doesn't matter. I'm hopefully going to give you some ideas of how you might start and the sort of recipes that you can apply in your sort of introductory studies. And for those of you who have done loads of programming, I'll also give you some pointers of how you can do some flashier stuff. Okay, so if most future jobs currently performed by humans will be done more efficiently and safely by robots or artificial intelligence, I'm not sure that's a particularly nice future, but that's again a different question. I think there's a kind of a sweet spot between humans and machines, and sometimes we get there. You know, the sort of apps that tell you what the weather's going to do. That's a great way for hiking. That's a nice hybrid between person and machine. But I don't know, artificial intelligence to replace scientists and writers. I'm not sure about that, but that's to be discussed. However, regardless of whether that happens or not, wouldn't you want to be the person programming this technology rather than being the programmed? Okay, so there we go. So what's going to be in this course? There's going to be 10 sessions. We're going to start off with modeling motion, so mechanics. We're going to look at things like data analysis, models, experiments. We'll look at gravity and astro, waves and optics, and then go things like quantum, electromagnetism, special relativity, thermodynamics, and then we'll finish off with some chaos, and then we'll look at something like epidemiology and brief the challenge. So pretty much all the topics of physics, certainly that you'll see in the first couple of years at university and at school, we're going to touch upon in this course. All right, and then we'll release the challenge in March, and you'll have till August to do it. Okay, so where can you find stuff? Well, this is the BPHO website. This is a link to it, and that's hopefully how you've entered it. You got here today. There will be some resources that you can get hold of alongside all the other good stuff which is on the BFO website. I also have my my book. So this is the one that was published a few years ago. This is sort of a slightly different series of projects. There are quite a lot of physics in this, but it's mostly kind of applied maths. But it has the advantage of actually being available, whereas Volume 2 will follow pretty much the course that we're talking about today. And Volume 3 will also be things like quantum mechanics, special relativity, and astrophysics. So, but Volume 2 is getting quite close to being published. And you can get it from World Scientific and other quality booksellers. So this is my website, the Eclecticon, and the idea is you look at the courses page. There's lots of other physics stuff too for free you can download. And if you go to courses, computational physics challenge, and you'll get, I think that might be the end of the presentation, this page here, which is this page. I don't know if I can bring it up. This one, all right. So you can download all the individual presentations, obviously the whole lot, and that's what you can get from the BFO website too. You can download some MATLAB apps and code, though you might wish to program stuff yourself in Python, etc. You've got a link to the book, and there's a link to the BFO website itself. And if you're super keen and want to find out what we did last year, I've got the other presentations and some videos and code too. So, and in fact, the challenges for 2022 and 2023. So pretty much everything you might want associated with this is from this page. So before we start, are there any questions about the sort of course, what's going to happen, what it's about, that has appeared in the Q&A? Coy, do you want to field anything that's come this way?
Most of them have been answered, but it's just questions about timelines. So that's fine.
Fantastic, brilliant. Right, well, okay, so in that case, what we'll do is we'll make a start. So I think if you do have a question, particularly if it's one of the hang on a minute, stop, go back, I missed something. Can you let the lovely Coy know, and he will relay that to me. So, okay, so let's go and can I just check the screen is nice and visible?
It is.
Fantastic. So session 1, models of motion. So we're going to start off. We're basically going to do this via some stories. So this is how I introduce kinematics. Kinema being, motion basically in Greek. And for those of you, anyone from Winchester, my students, you will have probably seen this if I've taught you in the last few years. So this is Usain Bolt, still the world's fastest human. Well, certainly the ones that we have data for that's been measured. So he broke the world record for 100 meters in 2008 and indeed in 2009. That's what he looks like, or looked like at the time. Maybe he has a beard now. And I think this is the Olympics in London, which he won in a spectacularly fast time. So the world record was 9.69 seconds and 9.58 seconds in Berlin. So that's currently still the world record. So in kinematics, you might ask, well, you know, how fast did he run? What's that all about? How would we work out those things? So the first thing you might want to do is get some data. So a very nice, I think it's an Australian chap, got the video, and every 10 meters, and you can see some lines drawn on the track here. For those of you who've done some running, basically what happens is that he went through the video frame by frame and recorded the time when Usain Bolt crossed a 10-meter line. And these are the times we've got here. So if you've done some video motion capture in your physics classes, that's a really good way of looking at kinematics. You can drop balls, you can juggle things, all sorts of stuff. And if you haven't done that and you're allowed a smartphone or in your laboratory, this is a great way of doing some basic physics. So now if you plot that, you'll notice that it's not entirely straight. So see the gradient of this, the rate of change of displacement is the velocity. We can clearly see that that is changing versus time. All right, so how fast did he run? It kind of depends on what time we're talking about. So what might we do? Well, given this data, if we just literally had it in front of us and we had a ruler, we might draw the largest triangle we can possibly draw, all right, and do delta x over delta t, all right, at a tangent to any point, and that would be the speed at that particular point. It's velocity because we're talking about direction in one motion. But that's going to be pretty tedious, right? What happens if we want to do it maybe at 100 different points here? In fact, how have I made a curve in the first place? So what I've done is fitted something called a cubic spline between the data points. This is a cubic equation which takes every 4 data points and fits a curve such that the gradients are the same. So that, well, not the same, but they are sort of smooth between the points. So this is a recipe you can find. Most languages will allow you to do this. If that was a bit too much, you can fit quadratics or possibly even straight line graphs. So this is called interpolation. That's so project number 1 might be to take data like this and see if you can make a smooth curve between those points. Now, once you've got a cubic between continuous points, we can differentiate cubics, make quadratics, and that allows us to find velocity from our displacement versus time. So basically, I can do this. I can find the tangent at every point along this curve, and I can plot this. So I can go from this data to a graph of velocity versus time. And this is really interesting because we can kind of figure out what's going on here. So there we are. So I worked out local gradients calculated every second along a smooth curve rather than at every sort of 10-meter intervals. And so what happens is Usain sort of starts, so he blasts out at about 4 meters per second and rises to about 11.5 meters per second. Then something really interesting happens. He seems to slow down, all right? So I think maybe there's a little bit of aerodynamic braking there. And then he keeps accelerating and then reaches a sort of plateau, a sort of constant speed, which he maintains for, well, nearly sort of 5 seconds. And I think that's what differentiates him in the other sense of differentiation from other athletes, because other athletes are slowing down, whereas Usain Bolt is able to maintain his speed. We can see that from the data. Now, it's probably a bit old for some of you guys and girls, but Usain Bolt infamously put his hands in the air in sort of a euphoric victory and sort of sauntered across the line while breaking the world record in Beijing. It's an extraordinary experience. And you can actually see that looking at his velocity decreasing in the last sort of second, which he thankfully didn't do in Berlin. So there we go. And then we might want to differentiate it again. In other words, finds the gradients at all points. And this is acceleration versus time. So acceleration will then give us force because mass times acceleration is vector sum of force. And what you can see is a maximum acceleration, and then there's kind of a bit of noise. All right, so we don't really have the data to really know that we've got some up and downs here. Although we do have definitely a negative acceleration for Beijing, where he's slowing down. So there we are. So once we've got distance versus time, you find the gradient twice, you get acceleration. And if you multiply that by Usain Bolt's mass, you've got the force on him, the net force. That's really interesting because you could then use that to kind of understand how, the forces on his muscle that his muscles exert. You could relate that to weight training, to food, to muscular performance, all sorts of sports science. Okay, so there we go. So from kinematics, from this kind of data of distance and time, we can work out all sorts of interesting stuff. Okay, so here we go. Here's the sort of complete view. And I've used the same time scale so you can compare the graphs. These graphs were all produced from a MATLAB program, which read in the data and then performed my cubic splines and plotted the data and made it all look nice. Okay, so this is sort of data pipeline is something that I'd recommend you get into. So if you're starting out and you've never programmed before, probably do something in Excel would be a good idea. But you want to get something like that has a graph plotting capability. So matplotlib in Python is a good thing to do. Loads of different things, different languages. So there we are. Number two, we might sort of apply the same idea, but perhaps a different situation. So this is Jeff Bezos with his Blue Origin project for sending possibly tourists, albeit rather wealthy tourists, into space. And it's probably hard to see the actual numbers here, but what I did is I watched his video and every sort of few seconds wrote down from the telemetry the altitude in feet and the velocity in miles per hour. And I've converted these in Excel. This is an Excel sheet screenshot into how far up he's gone. So X is the altitude in kilometers, the velocity in meters per second that's going up, and the acceleration that's going up. And if you plot that, you see some rather interesting things. So this is pure Excel. You could do this in a computer program, but obviously you need to get the data in the first place. I think there should be this data available if you sort of click on the download links. So if you plot altitude versus time, we have a nice almost sort of parabolic trajectory. And I can tell you it's parabolic because the gradient of that is a constant, sort of, well, certainly between about 110 and about, about 380 seconds. So he's going to be in free fall, or the rocket is in free fall. And the gradient of that graph is pretty much G. So if you look at the acceleration versus time, very close to 9.81 meters per second squared. There's a bit of a glitch in the middle. I'm not sure what that's all about. But anyway, and then of course, you can sort of see some slightly different accelerations as he's going up into space and also sort of coming back down to Earth. So how have we worked out the gradients? Well, in an even simpler way than by fitting cubic splines. Literally, we've done the difference in velocity. So Ti means the ith time, and the velocity, that's the previous velocity, and I'm dividing that by the change in time. So that's how I've got acceleration from my velocity. I found my velocity by just converting my miles an hour into meters per second. So there we go. So that's a nice sort of simple thing you can do, but that's a sort of quite a major moment for humans, and so you can actually sort of use that data off the internet to create these kind of graphs. So there we are. That's actually the team, and I think that's one of the oldest astronauts. And there we go. That's the sort of Blue Origin exploration. So, in summary, so kinematics, it gives you a really good reason to know velocity or acceleration from displacement measurements. All right, so the gradient of the underlying curve. So we may not know the functional form of the curve, however. We're going to have to estimate it from the data. So for Usain Bolt, the velocity time graph is not straight. You could make a model, and that could be a linear bit and then a straight line bit. Okay, so what's nice is we can get the data, and then we could say, how can we simplify it? So we could do some maths and some analysis. So we could use the data and our analysis of it to then create some simpler models, which we can use, calculus or all the tools that we already know. Okay, so in my Bezos example, I'm assuming a straight line between my velocity measurements, and that's how I've gone from velocity to acceleration. Whereas my Bolt example, I fitted a cubic between my distance versus time measurements, and then I've used that to work out the gradients of that curve and the gradient of the gradient. Okay, so there we are. This is a form of numerical calculus. If you're starting out, and if you're those of you who are not in the sixth form and have done no calculus yet, and you think that sounds interesting, but I haven't studied this yet, then literally doing the difference in velocity over the difference in time will give you your acceleration numerically. And that's perfectly good as long as your time difference is quite small. Okay, so before we go to the next one, are there any questions about these sort of kinematic ideas?
No, there was a question about plotting graphs. If you're using Python, what's a good graph plotter?
Right, so Python, Python has some libraries, something called matplotlib, okay, matplotlib, matplot library, if you like. And the mat also could be like MATLAB. So there's aspects of Python, the NumPy library, which will turn Python into something that looks a bit like MATLAB. And MATLAB is a really nice sort of high-level language, which if you know a bit of maths, you can probably code. So I'm going to show you some things in MATLAB. It's much a standard in engineering, which is my professional background before I became a teacher. But obviously it's not entirely free. So whereas Python is. So that's how a lot of people start. So matplotlib is a good one, but there are many other. I'm not going to say to you, oh yes, use this language, because everyone will have their own favorites. And in fact, in the challenge, we don't specify a particular language. Basically pick one you like or what someone can teach you. However, I do recommend MATLAB. The student version costs about £30 and you've got all the libraries you could ever want. Okay, so we're going to do the bouncing ball simulation. So this is a little bit of coding. And I think this is something where we can talk through how a bit of coding works. So firstly, let's just run this little thing, and then I explain what this all means. So basically, we're bouncing a ball. This is my MATLAB environment. So you can download all of the code via the Eclecticon. If I just go back here, so if you click on code, right, you'll get everything that's in this directory. There's hundreds and hundreds of bits and bobs. And if I go to physics, to linear mechanics and ball bounce, and I click on ballbounce.m, oops, that's a bit small. So there we go. Let me make that a bit smaller. So it's a bit quick. We made two pictures of the velocity time graph and the displacement time graph, and then it animates all of these. So we drop the ball from here, and it bounces up and down. There we go. I don't know how the frame rate over zoom makes that look, but there we go. We've got a little bouncy ball clock. Okay, so it's not such a bad model of reality. We've got something called a coefficient of restitution. So the speed of separation of the speed of approach is 80%. All right, so it's losing a bit of energy per bounce. Okay, so how might we implement one of these sort of things? So basically, let me just go back to here. And this is kind of the idea of science by simulation, is that if you want to build a simulation of this system, you're going to have to think about what all the inputs are, and then kind of what variables you might have. So you're creating your own little universe. That's a nice thing to do, all right? Because these kind of computers are not very intelligent, but they obey your commands without getting bored. And I think that's a really good relationship, I think. So what we're going to do is we're going to define x as the distance that goes up here. I think ignore the x and the y. The x here is the height of my ball. So t is time, v is velocity, and I've assigned letters to these, just like you do for algebra. I've got g is 9.81, and my time interval dt is 0.01 seconds. So everything's in standard units. My coefficient of restitution, the speed of separation of the speed of approach, is 0.8. So I've assigned things just like you would see in algebra. The semicolon is a MATLAB thing, and that means it doesn't display to the command window that we saw earlier. All right. And I've got two other things. I'm going to set the number of bounces to be 50, and I'm going to have a bounce count, or a counter, which starts at 0. So obviously, I don't want this will bounce infinitely number of times, although they're large. So I'm going to set the bounces to be 50, so it doesn't. So the actual program will stop. So there we go. What we've got is a loop here. So what I'm doing is in MATLAB, we have what we call a while loop. Now, I have a slightly different syntax. In the end, in blue, we're going to go round this thing as many times until the bounce number exceeds max bounce. Okay, so this will go around this loop 50 times, and this will happen really quickly. Okay, so what happens? Well, I'm going to use SUVAT, constant acceleration motion. So eyeball, what I'm sort of highlighting at the moment, and hopefully you'll see that ut plus a half at squared is what I'm removing from my height. Okay, so basically my velocity is going to be sort of So which way am I doing? I think so yes, my velocity is going to be v is positive downwards. Okay, so if you look at the velocity step, I've got the previous velocity plus g delta t. Okay, so I'm gravity acts downwards. That's how I'm increasing my velocity. All right, so the second step should be fairly obvious. This looks like a kind of iteration, and the bit in brackets is telling you the next element in an array. You think, what is an array? Think a spreadsheet. So if I just go back a few pages, so for example, this could be my time array. The first one might be 0, the next one's 8, the next one's 19, etc. So time 1 would be 0, time 2, 8, time 3, 19, that kind of thing. So in MATLAB or any language, we're thinking about creating spreadsheets. So I'm going to increment my time variable as well. That's going to add the next element of time. And I'm going to subtract basically the sort of how far it's moving in terms of its velocity and acceleration from my original height. So that's going to go down and down and down, faster and faster. But what happens when it hits the floor? Well, this is the fun bit. So if my displacement becomes negative, so it just starts to go within the floor, obviously it won't actually do that, but the next iteration is negative. And importantly, my velocity is going downwards. All right, so the velocity is positive. So the next velocity that I calculate is bigger than 0. It's going downwards. I'll add 1 to my bounce number, and then I'm going to change my velocity, all right, to be the negative version. I'm going to flip the sign, and I'm going to multiply it by my coefficient of restitution. So if it hits the floor at 10 meters per second, once it's bounced, it will go up at 8 meters per second, but going up rather than down. And that's it. So the next loop, your velocity is, of course, now going up. So that violates this criteria. So we don't have any more bounces. So it only bounces once it's gone up and then back down again. All right, so that's pretty simple. It's a sort of a beautiful simplicity to the logic of what's happening here. And that's really what's wonderful about coding, that everything has got to be there, but it doesn't have to be verbose. And the other thing we also need is we need to increment our index, so n goes to n+1. Now there's loads of ways of doing this in different languages. Some of you might know an even more efficient way of doing this, but I think this is sort of fairly clear about sort of the essence of what's going on. The other thing we want to know is if we've done a bit of maths, and I'll show you very briefly what that might be. We won't go through it in detail, but I'll give you a pointer to it. So I don't know if we can sort of read this, but 2 times the square root of the original height times 2 over g times 1 over 1 minus the coefficient of restitution minus a half. That is the total time to stop bouncing, all right, which turns out to be about 4.06 seconds. So in other words, I've worked out something about the whole motion. And though I've not given it here, you can also work out the total distance that the ball travels, which is about 4.6 meters. So there we go. And then there's a bit of code here, which is all about plotting the graph. And every language will have its own one. All right, but you can sort of things like I'm plotting time versus velocity. I've got some labels, and I might print a PNG file from it, something like that. Okay, so with a few other bits that are missing, pretty much that is what created that animation. So I think I'll just sort of just give a very little nod to how you might model this mathematically. But this is something you want to look at in slow time with a nice cup of coffee and possibly a friend, or how you might do it. So this is the mathematical modeling. So we've got a ball dropping here. So it gains, so the MGH is the sort of gravitational potential energy it loses, or you can use SUVAT. And if you work out what the velocity is, that's going to be root 2gh. So half mv squared is mgh. And then we're multiplying that by a coefficient of restitution. So that's the velocity that it bounces with. So it will go up, all right, because v squared is going to be 2gh, as it were. So the height it reaches will be c squared times the original height. So our velocities will scale by c, and our height scale by c squared. So what we end up finding to work out the distance travelled, so h plus c squared h and another c squared h, etc., turns out to be a geometric progression, which is rather nice. And we can use the formula for the sum of a geometric progression to work out how far that actually goes. Because in the limit of infinite number of bounces, then that c to the 2n will disappear because c is going to be less than 1. So we end up with this. That's the formula we used to calculate this. The time is very similar, which the time is root 2h over g from kinematics. And then each time we're going to multiply that by the coefficient of restitution, right? Because it involves the sort of the speed here. So that's also a geometric progression, but it's not quite the same numbers in front. You have the same factor here, but rather than 2h, we've got 2 root 2h on g. So again, that's something to eyeball in slow time, but that's now a formula that we can use to predict how long it takes to bounce. And a really nice thing to do is to work out the coefficient of restitution for your given ball, or basketball, tennis ball, etc., from the time it takes to bounce. So if you drop a ball from, say, a meter, use a stopwatch to find how long it takes to bounce, rearrange this formula, and you've got the coefficient of restitution. So that's a really good experiment to do. I probably would measure it, 4 or 5 times and take an average, but that's a pretty good way of working out the speed of separation over the speed of approach. Okay, so before we go on, are there any questions on this kind of little model? Any that have come out in the chat?
Would you like to quickly just explain what DT is?
Sure, yeah. So what I'm doing is I'm stepping through time in this simulation. So if you have a look at the graph, it looks really smooth, doesn't it? So this is the height of the ball versus time. I've got these lovely inverted parabola here. And this is the velocity time graph. My velocity is sort of actually I'm flipping this. This would be the velocity upwards in this case, so it's negative as it's falling. And what I'm doing is I'm evolving through time, and my time interval is so small you can't actually see the steps in the graph. All right, it's every thousandth of a second. So every thousandth of a second, I'm adding an extra element in my spreadsheet, although it's an internal spreadsheet. It's what we call an array, or a list of numbers. So my time will start off as 0. The next one will be 0.01 seconds. The next time will be 0.002 seconds, etc. All right, so dt is my fixed interval of time. Okay, if that's all right. Any more questions? Excellent. Right. Okay, so here is a really cool demonstration. So all you need is a basketball and a tennis ball. Other balls are possible, but I kind of recommend it with that pairing. And if you drop these from rest, and I have a little video on the Eclecticon of this, you'll get a surprising result that the tennis ball will fire up and possibly even hit the ceiling. So in the ratio where the mass of the basketball is much, much bigger than the mass of the little ball on the front, and all the collisions are elastic, it turns out that you'll go up to 9 times the distance fallen. So if you work it all out and you conserve momentum and that kind of thing, so these are the coefficient of restitution between the 2 balls, and the other one is between the big ball and the ground. You get this sort of rather complicated ratio of the final height to the original height. And if everything's elastic, it turns out to be this. I think you can, if you sort of eyeball this, if you let C1 and C2 is 1, we've got 1 plus 1 plus 1, that's the 3. And that results in this formula here. And if that ratio I'm highlighting is 0, in other words, that little ball is really tiny compared to the big one, that's h over h is 3 squared, or 9. Okay, so we got to 9 times the original height. So a nice thing to do is to actually make a calculator from this, because this would be quite a complicated thing to do every time. So there we go. You might want to make a spreadsheet. So again, if you're really new, oh, by the way, if you download the presentation, click on that link, you can see me doing this experiment with a basketball and tennis ball. So probably the first thing I would do if you're very new to computing, or even if you're an old hand and want to make a model, is once you've kind of understood the physics, put it into Excel. And then you've got all the inputs really clearly written out. So our masses of the balls. So, and I did this experiment in the class. It's 595 grams for the basketball, 57 grams for the tennis ball. These are my coefficients of restitution, which I can find by dropping the basketball and timing it, how long it takes to stop, and the formula we saw earlier. Or it's a bit harder for the tennis ball on the basketball because it tends to fall off, but you can make an estimate. I can drop it from a meter or whatever I want, and then I can use my formula to predict that height given these numbers here. All right, so that formula is essentially what's inside this cell. And there we go. So I've got these sort of predicted rise of these things here. Okay, so that's the ratios of the basketball and the tennis ball. Okay, right, there we go. So do I mean that one? That's interesting. Of a drop height. I'm not sure. I think that might be the very first one. Yeah, that would make sense. So this is from my sort of that's my first bounce, whereas actually that's the that would be, I think that's right, isn't it? I'll have to double check that. I think that's just using the sort of a coefficient of restitution. But this is the predicted height of my tennis ball, my double ball bounce, just under 3.6 meters. Okay, so that should probably hit the ceiling in your classroom. Yeah, so I think I'll skip over this, but this is the actual maths of it. I think sort of something has happened to my algebra here. But if you download the presentation, you can work through this all yourself. Right, so in terms of collisions, sort of like with sort of momentum, it turns out there's a rather nice way of doing this. Now, when you've done sort of collisions, particularly those who are doing A-level, you'll probably look at restitution and work out whether it's a sort of an elastic or an inelastic collision. You'll conserve momentum, the mass times the velocity. But when you do two-dimensional, three-dimensional collisions, you might go, wow, that's a bit complicated. There's lots of variables here. So there's a really nifty way of doing this, which is, I'm pretty sure is embedded in every single computer game that involves you colliding a car with another car or another person or a ball or whatever. And it uses something called the zero momentum frame. And basically what you do is you do the mass weighted average of your velocities, and then you apply it in this little formula here. So U is the original velocities for mass 1 or 2. V is this quantity here, and this is your coefficient of restitution. So this is a vector equation, and you use that to work out what happens next. So I've written that in a little app, which I sort of use to torture my students with in terms of working out various problems. So in this case, what happens next, V1 is -7/10 and 0.8. That's the X, and that's the Y velocity here. And you can encode this into a nice little simulation. So I have you can download this one. So let's have a look. It is in MATLAB. So if I go to ball bounce, and I think it's this one. No, that's the one we looked at before. Right, so it's balls in a box. There we are. All right, here we go. So, and this is really fun. It all looks so real. And what I've done is I've got sort of random conditions. I think it starts to, does it reset? There we go. So we've got two balls and they kind of bounce against each other, and it bounces off the walls. And eventually, because the coefficient of restitution is not 1, it will sort of settle down. So, this is rather fun. But ultimately, it looks like this would be really complicated to work out. But actually, it isn't at all. All you're doing is you're applying this formula here to work out what happens when those things collide. There's a slight caveat that you have to sort of work out whether a collision happens, and you can do that by basically working out the distance between the centres of these balls. And when that distance, using Pythagoras, is less than the sum of their radii, then they have a collision. Then you can apply this to the velocities. But ultimately, it's exactly the same as what happened previously. That's that we can evolve time like we did in this example. And if you want, you can have some gravity too, so you can get things to sort of fall to the bottom. I can't remember where I've set that in this particular box. So there we go. Right, let's go and have a look. What else we got? So there we go. There's another picture of the zero momentum frame. So the way this works is that essentially what you do is you have a frame of reference which moves at this speed. And if you do that, so you imagine you're looking at a collision and you're moving past them at this speed, the collision looks a bit like this. All right, it may not sort of be in the x-axis, but essentially the balls will be approaching each other such that the net momentum is 0. So they must have equal and opposite momenta. And so when they recoil, all we have to do is just multiply that by the coefficient of restitution. And then to transform back into the real frame, we just need to add our zero momentum frame velocity. So that explains the formula that we saw. So there we go. That's hopefully a bit of fun. Right, so in the last few minutes, let's kind of have a look at mechanics. So this is an app. So this is a bit more than just, you know, an Excel sheet or a bit of code to run and applicate. This is something that's a bit more, you might even put into a phone app. So let me go and run this. So you can download all of these if you have MATLAB, but there are lots of programs where you can create your own applications, but perhaps this isn't the first thing you'd want to do. All right, this is perhaps something when you're a bit more experienced with computer programming. So I've got loads of little apps here. Slope is the one we're looking at. So if I run Slope, and I think apps is a wonderful things basically, because it allows you to create something which gives you just what you want and nothing else. Okay, so we've got Newton's second law. Mass times acceleration is the vector sum of force. Best law of physics. Right? And then we've got a slope here. Now, if I fix the scale, so I can change the angle of the slope. So all my inputs are defined in my app and nothing else. Okay. So essentially what we're doing is solving every single something on a slope mechanics problem that you could think of. And it's visually changing. So there's lots of ways of changing my inputs. I can type in here, I can make that 42, for example. All right, or I can use my little buttons. And if it's on a mobile phone, you can maybe use gestures for this. We can change the coefficient of friction, because this cat is sliding on this one. So at the moment, the cat is accelerating down the hill at 2.48 meters per second squared. So how do we work this out? Well, we've got a vector sum of the forces. Let's show that mass times acceleration. This is a really good way of exploring what's going on and calculating all these things. So that's the weight of the cat, 39.2 newtons. The mass of the cat, which we've got here, 4 kilograms, quite a big cat. And the strength of gravity, that gives you 39.2. So let's make that 10, just so you can sort of believe that I've got all the right numbers. We've got friction, so the coefficient of friction times the normal contact force. And that's the red one. And we've got the tension. So I've got a little rope. So if I increase my rope tension, I can actually change the situation dynamically. And you can see this vector sum of forces, the red, the green, the blue, and the magenta, ending up with this mass times acceleration down the slope. So I increase my rope tension. What we'll find is eventually it will start to get into an equilibrium. Okay, so there we go. My mass times acceleration is disappearing. And now we are in equilibrium. Look at that. All right, so static friction acting uphill. So it's kind of coming downhill, friction's acting uphill. And as I keep my tension increasing, eventually my friction will change direction. And now, as I keep my tension getting bigger, now we're starting to get some acceleration uphill. If I just sort of remove my fixed axis scale and do that again, there you go. All right, so there we are. I think that's as fast as it goes. So there we are. So and now mine accelerating uphill. So there we are. I think I've set it so if the tension gets any bigger, the cat will be drawn off the slope, and then that won't be so much fun. So this is an idea that everything about this problem you can put into an app. All the graphs, the vector sum of all the forces, all the things you might want to calculate, everything is there. And that's quite a nice thing to kind of have as a projects. We saw last year and the previous year with the sort of orbits and also the atmospheric models. People made phone apps just a bit like this. Okay, so what else we got? This is a bit small to see. This is a water rocket, and what we're doing here, so this is perhaps a more for sick form. This is Newton's second law in differential equation form. So this is the mass times the acceleration, and that means the gradient of the velocity versus time. And that's the vector sum of the forces, the thrust, the weight, and this is a formula for drag. So I was teaching, I don't know if any of my students in the fourth year are here tonight. Hello. So this is what we just met today. So it's goes as the square of the speed. And what I've got here is the speed, well, the velocity times the magnitude of the velocity. And that means the drag always opposes motion. All right. So for a water rocket, of course, we've got thrust. So before we eject all the water, we might have the mass flow rate times the speed that the water is ejected. That's a good model of the rate of change of momentum, so the thrust. And the mass, of course, as it loses water, the mass will reduce. So m will get smaller. And if we reduce, say mu is, say, I know, 1 kilogram per second. So after a second, we've removed 1 kilogram of water. And of course, that will happen until we run out of water, and then we fix our rocket mass. So this looks quite complicated, but what we can do is we can actually just stick it in a loop like we had before. Now, this might be a bit small to see, but what you can have here is until we've hit the ground, I can work out the drag and I can work out the thrust. And once I've run out of water, the thrust is 0. And then I'm using SUVAT, ut plus a half at squared, between the time steps to work out what happens next. And then I plot some stuff. So if I actually plot this, what we find is this particular rocket went to about 60 meters, which was very impressive. It was in the air for about 7.6 seconds. And you have a huge acceleration temporarily as it's just about running out of water. And then obviously it then sort of approaches G as it's falling. So there we go. And then we've got our velocity, which sort of increases to a whopping 95 meters per second after about a second, and then reduces considerably as it starts to sort of just move as a projectile. So you might argue that this little glitch here of acceleration might be unfeasible, but given the modeling we've got, this allows you to understand the dynamics of my water rocket, which is quite cool, I think. So there we are. So pretty much anything you can write down a differential equation for, i.e. Newton 2, stick it in a loop with a fixed time interval. I've used a very small number of seconds, 0.0001 second. All right, we can figure out what happens next. So there we go. These are the tools for motion. Right, what else we got? So this is our last one, and then we'll take a few last questions. So this is a bit more advanced in terms of the actual analysis. So this is something that I think this is for kind of sick form only. But if you study some rotational motion, you can work out how things roll down a slope. And so I think it's probably best if I show you the animation of this, and then I'll kind of talk about this little static picture. So if you want to run this yourself, you go to MATLAB, Code, Physics, Rotational Dynamics, roll the loop, and if you right-click and run that, hopefully this will work. There you go. I'll just make that a bit bigger. I think this will probably, there we are. So what happened here? Let's just run that again. Does that run? I hope it will. So there we are. My ball is rolling. Okay, and I kind of loop the loop and then falls off. And this particular set of inputs is such that it lands bang on at 0, 0. So that's quite a fun problem to /gnarly problem to work out. Another one is, what is the minimum height so that I drop my ball and it rolls all the way around and keeps going all the way around and looping the loop. So I'll see if I can do that. So if I look at the settings, I want to make it all the way around. There we go. So I'm going to change my parameters here. Just save that and run it. And there we go. So hopefully it should go all the way around. And main contact. There we go. Oop, I've made my animation a bit too small. There we go. That's better. Oops. Let's go and find that again. There we are. So it should be just high enough, so it gets just enough velocity, and it makes it all the way around. There we go. And that stops the simulation. One more time. So again, a little bit more than just making Excel sheet, etc. We've got a plot routine, which we are then updating in a loop, which is making my animation. But essentially, it's kind of the same thing that we've met so far. We have a fixed time step. We work out what's going to happen next. So we're going to have to do some laws of physics on this to, Newton second, or to find out what happens to the velocity and displacement, etc. But ultimately, we can work out in intervals of, say, 0.001 seconds, what is it going to do next? All right. So there we go. Just go back to our presentation. So trial. So there we go. And in Science by Sim 2, I derived this rather interesting result. So you want to go all the way around. So if we're rolling, rho is 1, and let's assume it's going to be, say, a sphere. So sigma would be 2/5. Add that to 5. divided by circle, and k is the radius of my little circle. That's what the height needs to be bigger than in order to go all the way around. And to fall off and land here, so it becomes a projectile at this point, the 5 becomes a 7 and the 2 becomes a 4. There we go. So for those of you who are super keen on maths, that will keep you busy for a little while to work that out. But if you do tackle one of these problems, and you may not need to use a roll, you could just take a little like a bead sliding down a slope. That might be a bit easier to work out. So that's when sigma is my rho is 0. That's still really a really rather cool problem. So there we are. So I think that is the end of today's session, and we've just got a couple of minutes before we close. So are there any questions about, well, anything we've met today, or about the challenge, or what's coming next?
There were a couple questions about the ZMF, the zero momentum frame.
Yeah, sure. If I zoom back on this one. So, okay, yeah. What's the question about that?
It's just generally, what is the zero momentum frame, and then what is the zero momentum frame velocity, or big V?
Yeah. So, okay. So basically, well, firstly, why would we want to do this thing? So if I say I've got some collisions here, all right, that we used in our ball bounce model. So U1 and U2 are those velocities that I represent in this two-dimensional picture. V1 and V2 are the velocities that happen after the collision. And C is our coefficient of restitution, our ratio of speed of separation to speed of approach. So if you work out this quantity, which looks like a mass-weighted average of those initial velocities. So if you work out what that velocity is, you subtract it from these ones and then add that velocity to it, you'll work out what happens next. So that is kind of a recipe, if you like, to work out how a two-body collision will work. So what is this V? What does that actually mean? Well, if you were to sort of look at a collision frame, and if I was to sort of run the situation look at, and what you would find is it would look like the total momentum is 0. So basically what you do is you basically sort of subtract this velocity from all the velocities here, and you work out the total momentum of that frame, and you set that to be 0. When that is the case, V is this. So that's a nice bit of maths you can try. But what does it actually look like? Well, if we've got 0 momentum, then the momentum of this one must be equal and opposite to the momentum of this one, because the total momentum is 0. That's the only way it could be. So therefore, after a collision, all that happens is we just reverse the signs. Okay, the masses haven't changed, not transferred any mass. So therefore, we know in this frame of reference what my velocities are going to be. So all I have to do is then add the velocity to it to get back. And I think there should be a minus sign, I think, for my C there. So I think there might be a slight error in this one. Oh, no, I've changed V and U. So yeah, that's all right. That is consistent with what I've got here. So there we go. I hope that's you probably want to have a go in slow time and definitely try and prove that the velocity of your frame of reference has got to be this, such that the total momentum of your frame is 0. Okay, try that out. Any more questions?
Yes, there were some. There's a number of sort of quite heavy questions, but we'll try and keep it brief for the moment.
I'll try my best.
So there were some questions about the tasks to be done for each week. Where do they find the few tasks that might be?
Okay, so what I'd recommend, I've changed this a little bit this year. So there's probably how many we've had. So I mean, you'd have to spend your entire time between now and next week doing these if you want to do all of them. So what I would recommend is download this particular presentation and find one of these you think, oh, that really interests me, and I think my skills are roughly there. So if you're an expert and you're in the upper sixth, and you've got a BFO gold last year, and you think, you know what, I've just been studying rotational dynamics, I want to try this really hard problem, then you can try and solve this one and make yourself this app. So that would be like the ultimate. If you think, you know what, I'm really new to this, what's the first thing I could do? Well, I think actually this might be a good one, the double ball bounce. You can make yourself an Excel sheet, And so you can literally put some numbers in here. You could measure a basketball and a tennis ball, or try it with other things. And you can work out that cell there in terms of these numbers. All right. And a nice thing you can do in Excel is actually give that a letter. You can actually set in it. I don't know if I've quite got time for that today, but you can assign a variable to that cell C4. So actually this answer looks more like the maths we've got here. And then you can actually just use it as a calculator to predict one of these, and then see how close you are to reality. So that's probably the simplest one. A nice one might be, the sort of bouncing ball sim. That would be a really good, because this is classic A-level stuff. So to actually write this little bit of code. So if you were sort of want to do a bit of Python or MATLAB or whatever, basically coding this up in the language of your choice, that would be a really good thing to do. And see if you can get to plot these graphs. And then the next step is, once I've got that, I've got my array of X and V and T, etc. Can I maybe make an animated graph? So, you might find that's a bit too difficult for your language, or you might find there's an add-on which will allow you to do animations. But then, that's something you can then look up on the internet. How is it done? I think the important thing is that if you want to start coding and you do all the tutorials, it's really dull. Whereas we've now got an incentive. I want to build a bouncing ball simulation or a rocket simulation or whatever it is. And so you've got this incentive, this thing to try and do. What's the maths of it? Now, what does that mean in MATLAB or Python or C++? You can then go on the internet and find out how you do an array, for example, in Python, which is the equivalent to what I've got here. How do you plot a graph? And then you'll have the equivalent to this code here. So this is, you've got an incentive for finding the syntax that you want. And then you can code it up and see if it works. You might make a mistake and then you might correct it. And that's kind of how it works. And then before you know it, you actually know how to plot graphs. You know how to do this kind of thing. And suddenly your skills are really expanding. So I would recommend pick a project, try one of them, try and do it, pick something easy so you can get some success, and go from there. All right. Any more questions?
Well, just on that, the bouncing ball can actually be done in Excel. So if you're sort of advanced, so you have an idea what Python is, then that's fine. You can sort of use your Python frame and construct it there. But if you're kind of new to coding at all, you've not done this sort of thing, then you want to start on Excel, because it works. You can just load it up, it turns on, and you can put things in Excel. And the bouncing ball would work in Excel, but it's probably not the simplest thing to try out. So don't sort of say, I must learn some advanced coding techniques, and with something sort of fairly simple like the bouncing ball, use something which works well, like Excel, and you can build up your program. And on the way, you're learning these techniques, because Andy is not going to be showing you. He's not going to be teaching you the code, because that can't be done. That would just take too long. This is about ideas. There's lots and lots of ideas here. And you couldn't build all these in a month of Sundays if you're kind of new to all this stuff. So that they show you what's possible. So what you're going to do is actually do something probably less complicated, and you're going to do one of them. Have a go at something for next week, just to get your fingers in the water, and just see what you can do. But Excel's a good place to start. Don't sort of feel, I must find out about Python if you've not used it before. Week one is not the place to sort of just start on that. But if you've done some coding, that would be fine. But don't be too ambitious. There were questions about the process. The rolling ball and the bouncing ball, they're not done by having some fundamental equation. You just put the numbers in. They're done by iteration. So Andy will say more about the iteration process next week, but you'll see there that there's a DT. So what you do is just take a starting time with a velocity and a position, and after a short time interval, you can calculate the new velocity, knowing the acceleration, and therefore the new position, and so on. And you just run it along. So the equations are very simple, and it just goes round and round and round, recalculating. So that was in there, but of course, if it's not a familiar idea, you may have just missed it. So watch out for it next week, because a lot of this is just an iteration process, a step by step, seeing what the next value is and the next value and the next value, and then plotting it. We'll say something about the competition in due course. There's 10 weeks to go, so the competition is not the sort of thing we're going to talk about now, and team sizes and such like. And one or two wondering about the MATLAB. Python is free. You go to the Python page, and there's a proper Python site. You can download the appropriate software. It's all free. MATLAB is not free, but I think there's a free equivalent, isn't there?
Yeah, so this is how you might want to go. So I've got on the Eclecticon, so here's the computational challenge page. Whoops. And underneath that is a programming link, and there's all sorts of things here, but there's a Python Raspberry Pi page. So Replit is quite good. That's an online Python. Or you can actually, if you're allowed to install things on your computers, you can click on this. It takes you to python.org. And this is where you would download Python. And there's something called pip, which will allow you to install matplotlib and other bits and other libraries so you can plot graphs. So that'd be a nice place to start. I've also got I've got a few tutorials for here, and I've got some basic Python that you can download by clicking on these hyperlinks. There's also a little Excel course as well. So if you're really new to Excel, there's lots of sort of how-tos, and in fact some simple calculators. So a nice way to start is to kind of find something that someone's already done which looks a bit like what you want to try and achieve, and then edit it. Right, that's sometimes better than starting from scratch, is to sort of find, say, I've got a speed calculator here. Well, you could then just change that to be a double ball bounce calculator or something like that. Okay, so there we go. I think that's probably enough for today. So thank you very much indeed for your time. It's been a pleasure, and do come along next week at the same time, and we'll carry on and look at some more examples.
Brilliant. Thank you very much. Hope to see you all next week.